Again. Okay, so before the break, so we just looked at the general idea of like how to compute my measure, right? Like so node purity or impurity measure. Now I told you that there are three things. There are many possible measures, like, but we are going to discuss three measures. Okay, so first we will start with the idea of Gini index or Gini index. I don't know, like what. I don't exactly know what is the right pronunciation. Different people call it different way. Let's just call it Gini index. Okay, so now given a node T, okay, the Gini index of the node is defined as follows. Like it's basically 1 minus summation over j, p of j given t, the whole square. Okay, where p of j given t is the relative frequency of class j at node T. Is that clear? Now, let's try to understand what Gini is accomplishing, right? Like so, now imagine there are two classes, and I have 50-50 data set. Okay, so what would be the Gini index? So what I have is, let's say there's class 1 and class 2, and let's say there are 3 example and 3 example. Okay, now what would be my Gini index for this particular table? It's going to be 1 minus summation over j, which means I'm going to do summation over all possible classes. There are only 2 possible classes here. So for the first class, what is the frequency? Half. So it's half square minus what is the frequency for the second class? Half again, so half square. So it's 1 minus, okay, well, I will not do the calculation. So it's 1 minus half square minus half square, it's actually 0.5. Okay, now let us look at the other extreme. So let's say it is 0 and 6. So now what would be the Gini for this? It will be 1 minus 0 square minus 1 square, which is 0, right? So Gini index is basically from 0 all the way to 0.5. Okay, so when the data is completely mixed, like when you have 50-50 for all the classes, right? Like so, or equal distribution of all the classes, then you're going to have a Gini index of 0.5. Okay, so lower the better. Like so, you go to 0. So only way to go to 0 is when you have only one class. Even if you have one more example of another class, it's going to be greater than 0. Is that clear? So just to give you one more example, right? Like let's say I have C1 is equal to 0, sorry, 1, and C2 is equal to 5. Okay, so now the Gini here is going to be 1 minus, what is the frequency for the first one? 1/6 square minus 5/6 square, right? So this value is 0.278. Okay, now this kind of splitting based on Gini, right? Like so this is used in like some of the famous decision tree algorithms like CART or SLIC or Sprint. Okay, so as I mentioned before, we will not see the individual algorithms, like, but these individual algorithms only differ based on certain criteria, like what testing to use, whether it is binary or multivariate, and so on. Okay, now, so given a node, we know how to compute the Gini, right? So now, if we go back to this particular figure, okay, so I'm going to erase all these things so that it's easy for us to explain again. Okay, so if we go to this figure again, now given this node, the data set, we know how to compute P, right? So that is by using the Gini index formula. Similarly, we know how to compute M11, we know how to compute M12. This is Gini for this table, this is Gini for this table, and this is Gini for this table, right? Now, this is also easy equation. It's just subtraction, like so. So one thing that we haven't figured out yet is, given 2 Gini for 2 different tables, how do I merge them to come up with M2, right? So the idea is simple. We are going to take a weighted average of these 2 Gini. So where the weight is given by, I think, size of the data set. Okay, so basically, sorry, I should not say that. So basically, so Gini for a split is given. Let's say there are k partitions. Okay, and the Gini for the split is given by summation over I is equal to 1 to k ni by n Gini of I. Okay, where ni is basically number of records at the child node I, and n is the total number of records for the parent node. Is that clear? So it is just a weighted average. Like if I have to go back to this figure, now this M1, okay, M1 is going to be weighted average. Like so, it's going to be N1 by N of M11 plus N2 by N of M12, where N1 is number of examples in this particular table, N2 is number of examples in this particular table, and N is the number of examples in the parent table. Is that clear? All simple. So here is one example worked out for you. So in this case, the parent has 7 classes of C1 and 5 classes of C2. So you have the Gini here. And there is this one possible split, which splits the data into these 2 partitions. Okay. For each partition, you compute the Gini separately, and then you do the weighted Gini. And this is the gain. So by doing this split, my initial Gini of 0.486 became 0.361, right? So the gap between 0.486 and 0.361 is the gain by doing this split. Now I can do many such splits, pick the one which has the maximum gain, right? So now we actually have a solid algorithm to implement. Like so, you can compute this recursively and like create best splits and so on, right? So this is fine. Now, how do I do this for categorical attributes, and how do I do this for continuous attributes, right? Like so, for example, let's start with categorical attributes. Okay. So in this case, you have 3 options, like 3 values: family, sports, and luxury car. Okay. Now, there are many possibilities. Like so, either you go for a multi-way split, which gives you a Gini of this. Okay. Or you go for 2-way split. Now there are 2 possible 2-way splits. Okay. Now you can try all these 3 options and pick the one which has maximum gain. So which one would have maximum gain here? We don't know the parent Gini, but it doesn't matter, right? We can find which one would have the maximum gain. Huh? Which is the best split here based on Gini? The multi-way split, right? Like, so it's always lower the better. So this is going to be the best, right? Now, this is easy for categorical. You can try all possible combinations and pick the best one. Now, what about continuous attributes? So let's just talk about splitting binary in continuous attributes, okay? If I have to split binary, then there are many, many possible splits. For each split, you have to count the number of records in the left, count the number of records in the right, compute the Gini, and so on, right? Like so. Now, the simplest method to do this is you take the entire database of records, you consider all possible values, and count how many class 1, class 0 on the left side, class 1, class 2 on the right side, compute the Gini, right, and pick the least, like pick the one which has more gain, right? Like so. Now this is computationally very, very expensive approach, okay? However, there is actually an efficient way to do this, okay, which just requires one scan over the data set, okay? So which is explained here. So let's say we want to split annual income. Okay, so here is a simple algorithm. So the algorithm is this: you take all your examples, okay, first sort them based on annual incomes. In this case, I'm sorting it. These are the examples I have: 60, 70, 75, 85, and so on. Okay, now I can pick a splitting criteria which is in between two examples. Like, so for example, my first example is 60. So I can have one splitting which is below 60. Anything that you want, let's say 55. Okay. Then I can have another splitting criteria which is between these two. Another one between these two, and so on. Okay. Is that clear? So now you can actually make this yes or no count and incrementally update this for every split. And you can compute the Gini index as well. Okay. And pick the one which has the least Gini index. In this case, it happens to be 97K. So you can have one tree which takes the income. If it is less than 90K, so 97K, you go one side. If it is greater than or equal to 97K, you go another side. Is that clear? Okay. So I think this completes like algorithm. Now I showed all these things with Gini index as an example, but you could really use any other criteria. So let's see two other criteria. Like, so the second criteria is entropy. So entropy of P is defined as minus summation over J, P of J given T, log P of J given T. This is a classical definition for entropy. Okay, so like minus P log T. Okay, now we know that P of J given T is the relative frequency, right? So can someone tell me what would be the minimum and maximum value for this? Let's do some examples maybe. So let's go to the standard classical, like, sorry, what? Minus infinity to 0, no. So let's see some standard examples. Let's say 0, 6. This is the best possible configuration, right? So there is no entropy. Okay, so now the entropy here is defined as minus 0 log 0 minus 1 log 1, right? Is that right? Now we are going to consider anything that is not well defined to be 0. Okay, so this is going to become 0 minus 0. So this is 0. 0 is the minimum value for entropy. Okay, now sorry, maximum, no, 0 is the best thing that you could achieve with entropy. Okay, now let's consider C1 is equal to 3, C2 is equal to 3, which is the worst possible configuration, right? Like, so now entropy is defined as minus 1 over 2 log 1 over 2, right? Again, minus 1 over 2 log 1 over 2. So this is basically half log 2 plus half log 2, right? I'm bringing the minus inside. So this is nothing but log 2. I can actually generalize this. Like, if you have a 2-class problem, then the highest value is log 2. If you have a k-class problem, the highest value is log k. Is that clear? So you're going to have answers between 0 to log k. Is that clear? Now, the information gain is given by entropy of parent minus summation over I is equal to 1 to n, ni by n of entropy of the child. It is same as Gini index, like, except for the fact that we are using a different formula. But the whole table and like computation is similar. We are going to call this as information gain. Is that clear? Now this second criteria, right, like information gain or entropy. So this is used in algorithms like ID3 and C4.5. If you are using ID3 in École, then essentially you are using entropy and information gain to split the data. Is that clear? Okay. Now the third criteria is the idea of classification error. So the definition is simple. So the error of P is given by 1 minus max P of I given P, or P of J given T, since we are using J. Okay. Now, what does this mean? So this just means that, let's say something like C1, C2. Let's take both, the usual example, C1, C2, 3, 3. Okay. So in this case, my error is going to be 1 minus. I compute the frequencies. The frequencies here are 0 and 1. I take the maximum of that. So the maximum is 1, right? So 1 minus 1 is equal to 0. In this case, 1 minus maximum is half. So it's going to be a half, right? So this is called classification error because we are going to assume that the majority class is the actual class. The rest is impurity. So 1 minus frequency of the majority class is what the rest is, right? Like so that is going to be treated as impurity. Is that clear? Okay. Now we have seen 3 different measures, like for homogeneity, right? Like so, they are not very different. Okay, so they have similar trends. Like you can see all the 3 plotted here. Like so, what happens if everything is class 0 or everything is class 1? They all get 0 measure. Okay, so the maximum is achieved when you have 50-50. So when you have 50-50, you see that, well, some of them achieve 0.5, some of them achieve 1, like, but it doesn't really matter because they are all correlated. Is that clear? There's a question about what is the logarithm for entropy. I assume log 2, but it could be natural logarithm. I'm not sure. It doesn't matter, I guess, to some extent. Okay, so any questions about the criteria for picking? Any questions in the chat? Okay. So this is all good. Now, there is actually one disadvantage with all these metrics that we discussed so far, okay? So if you think about it, the goal is to have less impure split, right? Like some split which has more purity. Now, one way to achieve that is by doing as many fine-grained divisions as possible. Like so, basically, when you have more partitions, the chances of having impurity reduces. Okay. For example, if you go back to our customer example, right? Like so, where you had a customer ID and income and other things. If you compute information gain for customer ID, okay, so that is going to have maximum information gain. But that is not desired, right? Like so, we don't want customer ID to have the maximum measure, like because we know it's a wrong split. So how do I avoid this? So how do I discourage these measures to prefer things like customer ID? Maybe I'll go back. So there is always risk in going back. The video would stop. Okay, I'm here. Yeah, so if I compute whatever, like so I could use Gini or impurity or like frequency or entropy, this is going to have high gain, right? Because it has no impurity. But that is totally like against what we were hoping to achieve, right? Like, so how would I avoid this to happen? Yeah.
could have some kind of regularization that favors larger children.
Yeah, so you can have a regularizer which says you should prefer lesser number of partitions as possible, right? Okay. Now we will take the risk of going to the actual slide. Okay, we're almost there. Yeah, I think it was here, right? Yeah. Okay, so now one way to do that regularization is by using this idea of gain ratio. Okay, so gain ratio is defined as the gain which we already computed by using these metrics divided by split info. Okay, now what is split info? So split info is minus summation over I is equal to 1 to k ni by n log ni by n. So this is basically the entropy of partitioning. Okay, if I have too much entropy in partitioning, then it is not a good idea. Okay, so for example, customer ID would have very high value for split info. So since it is inversely proportional, whenever you have very high value for split info, you'll be penalized for that. Is that clear? So this kind of regularization using split info is used in C 4.5. Okay, so I think we answered the second question. So there's only one final question left, which will finish our complete algorithm. So which is when to stop splitting. Right? So can I just go all the way in the tree until I reach a class, like a situation where there is only examples from one class? So for the toy examples I showed, it looks like the right thing to do. But imagine you have 10,000 examples or 1,000,000 examples in your data, right? So now this tree is going to be extremely long, right? So now when do you stop, right? So as usual, like any other machine learning algorithm, you train more, you're going to overfit. Okay, so here is the overfitting scenario in decision trees. Okay, so you see that as you grow the tree, so the x-axis is the number of nodes in the tree. As you keep growing the tree, your training data accuracy, it keeps on increasing, as we already know. However, the test data accuracy is starting to decrease, right? In this case, the tree actually started overfitting even after 20 nodes. Okay, so now this means there is no use in growing the tree to the end. Okay, as the tree grows deeper, it will start overfitting to the errors and noise. Okay, even if there is no noise, right? So then the tree could still overfit to some correlations which only exist in training data but not in validation data. Okay, that is also not desirable, right? Now, maybe before we think about how to avoid overfitting here, can you guys guess whether this is an example for a parametric model or a non-parametric model? People can answer in chat. I will see that. So is decision tree a parametric model or a non-parametric model? Well, for that, you should first remember the previous lecture. Okay, I'll go one step back. Give me an example algorithm for parametric and non-parametric models.
Non-parametric like
Sorry?
non-parametric like KNN.
KNN is an example for non-parametric. Okay. Parametric? Anything, linear regression, GDA, anything, right? Okay. Okay, that's good. So now, is this a parametric model or a non-parametric model? Sorry? Non-parametric. So why would you call this as a non-parametric model? So what are the parameters of decision tree?
Yes or no?
So the tests, right? Like so. Now, as you can imagine, the number of tests grows as the size of the data set increases. You have a larger and larger data set, the number of tests is going to grow. So this is a non-parametric model. Okay, so it has infinite number of parameters. It's infinite because you can grow as much ever you want. But that also has the risk of overfitting. So how do I avoid overfitting? Well, like so now, any idea? So far we have learned a lot about overfitting. So how would I avoid this overfitting? Any ideas? Any? Yeah.
Just like the other models, you get the validation set and then you vary the number of parameters from nodes, number of nodes in the tree, and then you test this.
So basically, you maintain the validation set. Like you did this for linear regression with SGD, right? Like so, you maintain a validation set. You compute every time like the validation error. When you see the validation error is starting to decrease, you stop, right? Like early stopping, right? So there are two approaches to avoid this overfitting. Okay, one is early stopping, which is what we usually do. Okay, but there is also another thing that we can do with decision trees. Okay, which is the idea of allowing to overfit. Okay, and then post pruning. You can allow the tree to grow, then you can prune the tree like to your needs. Okay. Now for decision trees, the second option is the most popular one. Okay. So people always grow the trees and then prune. Okay. So I'll tell you the advantages like when we see how we are going to prune. Okay. So there are two possible ways for pruning. Okay. So one is called reduced error pruning. Okay. And the other one is called rule post pruning. Okay, so now let's look at how both the approaches. Let's talk about the idea of reduced error pruning. Okay, now let's say I have a hypothetical tree like this. Okay, it could be any test, binary, continuous, we don't care. Okay, so let's say I have a tree like this. Now, whenever you are here, like you're going to have a default class this side. Okay, now the idea of reduced error pruning is once you constructed the tree, you're going to start from the lowermost level. Okay, so for example, in this case, like I will consider, well, I'll consider this node. Okay, and I'll remove this node. When I'm removing this node, it means I'm actually removing the whole thing and putting a class here, like, okay, like it could be the majority class. So instead of having, so initially I had two possible decisions. I'm going to merge these two decisions into one node. Okay. Now I will compute the validation error. If the validation error actually improves because of this pruning, then I will permanently remove that node. If the validation error increases, okay, which means it's not a good idea to prune this node, I will keep this. Is that clear? Now, it is going to become more interesting as you go up. Okay, so like for example, like you will consider this node, which is also non-terminal, right? So which means you will be considering to prune the whole thing, right? Now, when you actually go up in the tree, right? Like so, for example, let's say I consider this particular node, the pink node. Okay, so when I consider the pink node, I'm actually going to prune the entire subtree and just consider one class there. Okay, as you go deeper and deeper, you're going to prune a large subtree. Okay, so you'll consider all possible pruning until the parent, like until the root node. Of course, not the root node, so below the root node. And anything that improves validation accuracy, you prune. Anything that hurts, you don't. Is that clear? That is the idea of reduced error pruning. Okay, this guarantees that none of the pruning affects the performance. Okay, Now,
By error, you mean one of the three metrics that we are using.
sorry, what?
By error, improving error, you mean the
Oh, no, no, no. By improving error, I mean computing the validation performance. So we finished training. So we have the tree. Now I remove a node, compute the validation performance.
yeah, by that performance. I mean, which metric? Gini or
It doesn't, no, metrics doesn't matter. Here we are worried about the accuracy in classification, not Gini or classification, like not Gini or in entropy. Okay, so here we are worrying about the task. Okay, so that is reduced error pruning. So here is the same old example that we saw, right? Like where there was overfitting, right? Now starting from here, I started pruning my tree. So as you can see that as we keep pruning, the performance again improves. And finally, here it saturates, so I'll stop pruning there. Is that clear? Now, this kind of pruning is helpful. Like whenever there are some coincidental regularities in the training set that are picked up by the tree, but that is not present in validation. Like, so for example, let's say there is a correlation in the test training set, which is not there in the test set, okay? Now, by removing this test, you will not lose any performance in validation set. So you could very well remove it. Occam's razor, right? Like, so you prefer the simplest hypothesis. So if removing something helps, remove it in all way. Is that clear? Any question about reduced error pruning? So there are some questions in the chat. Does a smaller number of nodes imply we are dropping out some of the features? Well, you're dropping out some of the test conditions, like, so which means you could drop out some features. Yes. There is also another question. Can we merge two attributes for pruning? What do you mean by merge? Oh, when you drop, you are dropping. You are not bringing the test to the top. Okay. So, okay, yeah.
When you reduce the error pruning, do we remove one node at a time and we remove the one that reduces the error the most, or do we do it all at once?
One at a time. So it's not an ideal thing. So, like, depending on the order in which you are removing, it could hurt or help. Okay. So now the second idea is the idea of rule post pruning. Okay. Now, what is rule post pruning? So again, in this case, we are going to allow the tree to overfit. Okay. Now, once you allow the tree to overfit, let us consider a hypothetical tree. In this time, I'm going to name the nodes. Okay. Let's just call it A, B, C, D, E, F, G. Okay, from here we have the final classes. Okay. Now, once I have a tree like this, my first step is I'm going to take this tree and I'm going to convert this into a set of rules. Okay, so how am I going to do that? So you can see that in the end of the tree, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible decisions, right? Which means I can actually construct 10 different rules. Okay, the first rule is A, B, D, H. It has some class. Okay, let's just to make things simple, I'm going to do this. Okay, so this is class 0. Okay, and my second rule is A, B, D. Okay, let's just call H bar for the right going right. Okay, so this is class 1. Now the third rule is A, B, D, I is class 0. And the fourth is A, B, D, I bar is class 1. Then you have A, B, E is class 0. Then you have A, B, E bar is class 1, and so on. Right? I can take my data set and I can construct it into, I can construct a set of rules based on the decision tree. Okay? So now I will consider every possible rule, okay, and try to remove. What happens if I remove this? How is it affecting the validation accuracy? What happens if I remove this? 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 And so on. Is that clear? Anything which helps me in removing, like in improving the validation accuracy, I'm going to do that removal. Is that clear? Now, can somebody tell me the advantage of doing something like this over reduced error prone? And also the disadvantage. So what is the advantage of doing this over reduced error pruning? Yeah.
We can keep a node that doesn't decrease a lot the error first, but then if we further go inside the node, we can find a
Yeah. So like one major advantage, as he rightly mentions, is like, for example, like let's consider node B. Okay. Node B has many functions here, right? Like, so it is responsible for 1, 2, 3, 4, 5, 6 paths in my tree, right? In the case of reduced error pruning, my pruning was very crude. Like, so I remove B completely, right? On the other hand, like with something like rule post pruning, I could just remove B for one of these 6, and I can keep the B for the rest, right? So this is more fine-grained pruning. And also here, as he mentioned, like, so you can remove something in the top without affecting the rest, right? Which is not possible with reduced error pruning. So that's the advantage. Now, what is the disadvantage?
time consuming.
Sorry?
Time consuming.
What is time consuming?
Because you have to do.
Oh,
You have to go through all.
this computation, okay, here's the thing. Decision trees are extremely fast to train when compared to other algorithms, okay? Because most of decision tree involves just counting and like executing rules, okay? So finding these combinations is not time consuming. Like also, like even if it is time consuming, you do it once, then you have that set of rules, right? So the big disadvantage here is once you do these kind of fine-grained removals, you cannot convert it back into tree easily. Okay, so imagine like you removed B only for one particular node, right? Like so this kind of breaks the tree structure, right? So the disadvantage here is now you have to live with the rules, not with the tree. Okay, so now this is your model. Okay, I'm using the wrong. Now this is your model. Okay, every time there is a new example, you have to run it through all the rules and pick a decision. Okay, so but of course you can, if there are more than one rule which is getting activated, then you have to do majority voting and all those things. Is that clear? However, the advantage is like once you convert it into rule, it is extremely readable. So for smaller size trees, converting it into rule have advantage. Like now you can actually interpret what your model is doing. Like so, which is very important in certain applications like medical or financial applications where decisions are costly, right? Like so you want to understand the reason behind the decision, like, and it is possible if you have rules. Is that clear? Now, in general, to summarize so far, okay, the biggest advantages of decision trees is, well, first of all, they are inexpensive to construct. Okay, so you can just do these things very fastly. You will see that when you're doing a scale-learn, okay, and they are also extremely fast during prediction, extremely fast in prediction. Okay, and they are also easy to interpret. Well, of course, only for small trees. Okay, and the other big advantage is they can actually handle all types of attributes easily. Okay, so there is actually another big advantage which I think I forgot to add in the notes. Okay, with decision trees, you can actually handle missing values very elegantly. Like you can have uncertainty over missing values that propagate over the tree. Okay, so it is possible with decision trees. Like, so for example, let's say I don't have a particular value for a record, then I can give half weight of that record to one table and half weight to other table. So there are many efficient ways to handle missing values in decision tree. We are not going to talk about this in the course. Like, so you can go read more about it if you want. But that is another advantage which decision trees have, while it is something not very easy to do with other algorithms. Is that clear? Okay. So this is what I hate. Like, so we have 10 minutes, and I have to start something new. It's okay. We are going to do it. Okay, so that concludes our discussion on decision trees. Okay, so we're not going to start something totally new. It's related. Like, so now we are going to. So far, we have seen a variety of algorithms, right? Like, so we have seen logistic regression, SVMs, GDA, k nearest neighbors, decision trees, and so on, right? Like, so now instead of seeing yet another algorithm, like, we are going to talk about another important problem, which is the idea of ensemble models. Okay, now this is a general technique of combining different machine learning models, like to make a unified prediction or combined prediction. Okay, so we are going to talk about why one should do it, how to do it, and everything. Probably not just this week, also next week. Okay, so but to go there, decision trees are actually very good starting point. Okay, now let's take this particular decision tree as an example. Okay, so here you actually see there is some x1, okay, feature. We don't care what the feature is. Now, if x1 is greater than θ1, you go this direction or you go this direction. Okay, then I have the second feature x2. If it is less than θ2, I go this direction or this direction. Okay, so in this case, like, there are only two features, x1 and x2. So once you go this place, you are again considering x2. So you go this way or this way. Again, you consider x1, you go this way or this way. Is that clear? Now, this is good. Now, depending on where you reach, right, there is a decision. Like, if it is a classification problem, there is a class value there. If it is a regression problem, there is a numerical value sitting there, right? So now in this particular tree, there happens to be 5 different decisions, A, B, C, D, E, right? Now, one way to understand what decision trees are trying to do is there are 5 mini classifiers sitting in the leaves. Okay, we are trying to reach one of the classifiers and use that classifier, right? Now let us try to look at the same thing in the data space. So here is my data set, which has 2 features, x1 and x2. Okay, now if x1 is less than theta, okay, then I go this side. Okay, and if x2 is less than θ2, right? So that is my region A. If x2 is greater than, then this is my region B. Similarly, region C, region D, and region E. Okay, so what is happening here? So my decision tree actually takes my data set or the entire space of data set. It divides it into 5 different regions. There are partitions of like 5 different partitions. Okay, now all that my decision tree is trying to do is starting from the root, it traverses a path and reaches one part of the data set. Okay, and for that particular part, we know the answer. The answer is one class, like it could be class 1 or class 2. Like, for example, just for example, let's say this is class 1, this is class 2, this is class 1, this is class 1, class 2, class 1. Okay, now once I go to that partition, then I tell, okay, this is class 1 or this is class 2. Is that clear? So in some sense, we have 5 different classifiers. We can consider these 5 classifiers as some 5 experts or 5 models. Okay, Now, depending on my data, I get to choose one of the models, and I'm using that model for making prediction. Is that clear? So even though there are 5 models, I'm using only 1 out of 5 models to make the prediction. It's a very hard split of the data points. Okay. So, however, if you consider this as having 5 different experts, right? Now, there is no reason why you should always ask only one expert for prediction. You can actually ask all the experts to make a prediction, or you can ask a subset of experts to make a prediction. Is that right? So, in some sense, like I'm kind of coming up with 5 different classifiers here, and I'm using only one at a time. But there is nothing stopping me from generalizing this idea and have 5 different classifiers and asking all the classifiers for their opinion. Now, I could even have weighted opinions. Like, so for example, let's say one classifier is an expert in one particular domain, and another classifier is an expert in another particular domain, and third classifier, an expert in both these domains. Okay. So then whenever I make the prediction, I can always ask the first and third for first domain, and second and third for the second domain, because the third classifier is an expert in both the domains. Is this idea clear? Right? So this is what the concept of ensemble methods is. Okay. So this is basically the idea of combining models. Okay. So one way to think about this is, let us say I have k different models. So 1 to k different models. Okay. Let x be the input and t be the target. Okay. This is a classification problem that we are thinking about. Okay. Now, if you remember, usually we would estimate p of t given x, right? Now we have k different models, so we are going to have k different predictions, but so we are going to condition based on the model number. Okay. Now my p of t given x is going to be summation over k is equal to 1 to capital K. Is it clear? Summation over k is equal to 1 to capital K, pi k of x multiplied by p of t given x comma k. Okay, where pi k of x is basically probability of k given x is the mixing coefficient. Okay. Now I have k different classifiers. Now pi k of x tell me how important is this classifier to make the prediction, and what is the prediction of the classifier. I take a weighted average of all these predictions. That is my final prediction. Yeah.
Here K represents the models before combining them or after combining them?
K is just the index of the model.
Okay, so before they're combined.
What do you mean by before or after?
Well, here we want to combine models, so we have a certain number of models.
Yes.
Is that number K, or K is the number of...
Yeah, that is the number K. So you first decide how many models you want to train. Let's say 5. Then K is equal to 1 to 5. Now, given a new data point x, you will first compute p of k given x. Okay, that tells you for this particular data point how much weightage I should give for the kth model. Okay, then you multiply that with the model's prediction. You take the weighted average. Is that clear? Any questions? So this idea of like taking weighted average of different experts, right? Like, so this is known as mixture of experts. Or MOE. Okay, so now there are many ways to combine. I can construct this mixture. Yeah, question?
Regarding what you said just before, in the case that we have some models that are experts in some cases, but not in other. Why do we need an average instead of the first, well, the tree you showed first? Because with the tree, there is some sort of preselection of the model.
Oh, but the tree is too hard, right? Like it's a very hard decision. Like you cannot share knowledge between experts if you're using the tree. So on the other hand, like here you can actually share knowledge. Like so, for example, like in the tree model example I gave about 2 domains, right? Like so, pi k of x could be very high for 2 models, but with decision tree, pi k of x is either 0 or 1. So it will be 1 only for one model, and it is going to be 0 for all other models, right? Like so, if you want to take decision tree and put it in the mixture of expert formulation, so you're going to have k different regions, and this pi k of x is going to be 1 only for one particular model. For the rest, it's going to be 0. On the other hand, this is just a generalization. Like now you can have any value. Okay, so probably we will stop here and talk more about how to combine models after a break. So maybe we will continue.